السلام عليكم. بسم الله. المحاضرة أو الجزء الثالث في الكورس بتاعنا، وده الجزء الأخير إن شاء الله. The last part, strike slave faults. In G201 we give a brief about strike slave faults, which this kind of faults usually be vertical, and the movement of fault blocks be parallel to the strike of the fault plane. If we look at this figure, we usually faults occur in conjugate pair of fracture planes, and usually make acute angle and obtuse angle. Maximum compression strength usually bisect the acute angle. In case of strike slave fault, the maximum compression strength be horizontal like this, and sigma 2, which intersection between two conjugate faults, be vertical. Okay. This is a typical strike slave fault, which is vertical fault plane, not dipping in any way. But in deep slave faults, usually fault dip in one direction, which is downstream direction, or upstream direction in case of reverse, tilted or inclined towards downstream direction in case of normal faults. But here in strike slave faults, we usually fault be vertical like this, and the two fault blocks move parallel to the strike of the fault plane. Okay, two figures show offset of horizontal pitting here and offset of inclined bit here. Some lines developed on the fault surface, or some ridges and grooves developed on the fault surface due to friction along the fault during the movement of fault blocks. On right side of slide, we find a field photo to this stria, which is called sometimes Slicken lines. This Slicken lines is horizontal Slicken lines with zero rack angle is the angle between the lineaments on the fault plane and the strike of the fault plane itself. So the strike of this fault is going in this way, and the Slicken lines here is parallel to it. So the rack angle of Slicken lines in case of strike slave fault is zero. This is pure strike slave fault. In some cases, strike slave movements may be combined with deep slave movement, and fault in this case is called oblique fault. In these photos, we find some troughs and some elevated or permanent areas in the fault plane, what's called ridges. This permanent part is أو الجزء الظاهر ده اسمه ridge، والجزء اللي داخل جوه ده اسمه groove. But we have groove and ridges on the fault plane due to also a movement among the faults. Okay, so we have two kinematic features on the fault plane. It's stria, which is horizontal, mean pure strike slave fault, and grooves, which is also horizontal, means pure strike slave fault. Okay. Strike slave fault are two types. Okay, two fault blocks, one on right side, right hand, and one in left hand. When the left block move towards me, it mean be sinistral or left lateral fault. Sinistral mean movement against or anti-clockwise. Okay. In another case is decastral, which means the movement is with clockwise. So the right hand block move towards me, it means right lateral fault. We have two types of strike slave fault: left lateral fault and right lateral fault. Left lateral means the left block move towards me. Okay, right lateral mean right block move towards me. Okay, what is it? Where we will find strike slave fault, or what is the tectonic setting of strike slave fault? Actually, strike slave faults are found in many tectonic settings. Okay, we'll start by the most common and most pronounced habitat of strike slave fault. That is boundary transform fault, like San Andreas fault, like Dead Sea transform fault. All of this fault is global and extended for a long time, and usually linked between two other types of clear boundary. Here in this example, or in the diagram, we find the transform boundary, structure transform boundary, linked between mid-ocean ridge, divergent play boundary, and subduction plate boundary. So convergent plate boundary. So the first habitat of Strax-Slip fault is a transform plate boundary. And we give in two examples: San Andreas fault in California and Dead Sea fault in Sinai and Jordan. Okay. Second example of Strax-Slip fault habitat is trench-linked Strax-Slip fault. Usually, trench is the deepest area in sea developed parallel to the subducted slab, unsubducted slab. Okay. And it took conversion some part of this overriding plates, this overriding plate and this subducted slab overriding plates escape along what's called trench-linked Strax-Slip fault. Okay. Third example is indented linked Strax-Slip fault. As a front of collisional place or compressional place, some special pattern of Strax-Slip fault developed. Okay, it's very common in Tibetan mountain, Gobi, Montali. These parts of our planet display very well developed system of indented linked Strax-Slip fault. Last place, we have also transform faults which cut mid-ocean ridges. Last example is intracrotonic Strax-Slip fault or interplate Strax-Slip faults. Okay, we didn't care about this. Structural pattern. As any fractural pattern, Strax-Slip faults also developed as short segments not linked in the initial state, and later on with displacement proceed, we will find this all of segments linked together through via ways. Okay, many ways. Okay, the first pattern of is initial pattern. Initial mean we have several segments of faults parallel to each other or overlapped. Relaying pattern is a pattern of how Strax-Slip fault developed. Okay, relaying maybe shift of fault segment from right to left and left to right and so on. Well, we have pronounced it left stepping, so mean I will go from this part to left and so on. Right stepping, another, I'm going to right and so on. Okay. Overstep is occurring in many ways of this. Maybe here in left stepping, you are overstepping, maybe relaying, stepping also. Termination of Strax-Slip fault usually has a horse tailing display like this. Okay, after that, if one of this segment linked to another segment, we can find what's called bend. Shift on the strike of the faults is bend. We have two types of bend, is releasing bend and restraining bend. Releasing bend mean if we subjected these arrows of movements, we find this part is subject to local extension. Okay, so it is releasing bend. If we subjected a reverse of movement on reverse sense of movement on a fault like this, we'll find this part of fault will subject to compression, so it's called restraining bend. Okay, Strax-Slip faults usually propagated upward with horizontal movement. This is a problem. Why horizontal movements not cut directly through the sedimentary units, but it makes some deformations, which called Strax-Slip fault association. Strax-Slip fault association, not Strax-Slip fault line only, but association of structure. Okay. This association, if you found this association, we can say there is Strax-Slip fault here, what's called master fault. Okay, this master fault is dashed line here like this, and we will draw a sphere. If we apply Strax-Slip movement on this dashed line like that, so in the first stage we have several initial faults developed. Okay, in this way. Later on, two conjugate faults will develop. Okay, each one of them make a angle from 15 to 30 around the master faults. It's called synthetic shear. Okay, opposite to the main master faults, or make angle with master fault, right angle with master fault is called antithetic shear. Usually synthetic shear have the same sense of the main shearing. Okay, if this shearing is right, I think it's right. Okay, so it's also this two synthetic shear will take right sense of movement, but the opposite in synthetic will take here is left sense of movement. Okay, due to if we look at this ellipse, we find a compression in this direction, extension in this direction. This ellipse compressed in this direction and extended in this direction. So normal to extension, some normal full extension fracture will be developed, and normal to compression, some reverse faults or reverse fractures or shear will develop in this way. Okay. Also folding be normal to perpendicular to the direction of compression. Okay, شباب. Okay. The structural fault is characterized by so-called self-similar architecture. What's the meaning of self-similar architecture? Self-similar mean repeating its pattern of fracturing from regional scale to mesoscale, outcrop scale median, to micro scale. So at different scale of observation, we'll find the same feature. Okay. So if we take this is the major anatomy of the structural fault zone. Okay, with some bends, some initial folds, and so on. Okay, horsetaling. If we take small area of it, it will give the same architecture. Okay, and so on and so on. If at all scales, we will find the same pattern of strike slip association. Okay. Okay. Before we have to, this is some examples of strike slip fault association. It usually strike slip is a narrow zone of deformations of all of structure we explained before. Okay, is a normal world example of strike slip association. Here, this slide is very important. How strike slip fault link to each other. Okay, we have two types of faults in strike slip. Okay, one dextral, one sinistral. Okay. Okay, but if we make this stepping is left stepping with dextral sense of movement. Look, it's dextral sense of movement because right look moving towards me, left look move away from me. Okay, so here, if we apply, so this area, which is the gray color, move up. This area with white color move down. So this bend subjected to local compression. So it's called contractional or restraining bend. Here in this place, this white area is moving towards me. This also this is so-called contraction step over, no bend because there is no linkage. So it's step over compression zone. Sorry. Here, this black is moving up, this white is moving down. So this bend is subject to extension or release. It's called releasing local extension, and it's called releasing or extensional bend. Here extension step over. On the other side, it will have the same geometry but reverse. Sinistral mean the left block move towards me, right block move away from me. And this, if it's stepping, is left stepping like this with sinistral movement. So this area is extensional or releasing bend. This is a step, left step. This is step over, extension step over. هنا يبقى contraction or releasing bend هنا and so on. Okay. Coming to differentiate between bends and step over. Bends mean linkage of two segments with fault segment, transfer fault segments, and this may be subjected to local extension. So it will be called releasing bend. Here, local compression, so it's called restraining bend. This slide is very important. I will ask you about, okay, releasing bend mean segments of faults along the strike slip fault which is subjected to local extension or local compression. You have to choose, and so on. Step over zone, it's the area of no linkage between no fault transfer fault linkage, but extension faults develop due to the overstep zone between two fault segments is subject to local extension. So this area is called pull apart basin. This area is called pop obstruction. So the area between two fault segments here is right lateral movements or dextral with left stepping will give pop up. Okay. If we take cross section here in along which one of beams, this is restraining beams, it will appear like this, like what's called flower structure. Okay. Flower structure along this is cross section. Our cross section here is a flower structure. Flower structure, because it's look like flower. If it crossing restraining bend, compressional bob-up structure or compressional duplex, it will give us what's called palm tree, like this. This is example from seismic section of palm tree. On seismic section or vertical section, it's difficult to define structural fault because the movement is horizontal. It was easy to define normal faults or reverse faults on a seismic line because there is vertical displacement. But in case of structural fault, it's difficult. But we have some criteria to define a structural fault on seismic line. First criteria is usually be vertical, not deep like this. When it's branched upward, making what's called a flower structure, it will convert to be slip fault, maybe reverse or normal. Here it's reverse because this marker is reflected here, so it's reverse fault. Okay, so it's look like palm tree, so positive flower structure. Okay, we'll say it positive flower structure. Another example, if we have cross section above releasing bend or extensional duplex or pull apart bend, will give us what's called negative flower structure or tulip structure, like tulip flower. Okay. This example of tulip structure on also we have vertical fault branched upward to flower. This flower with negative down movements, so it's called a positive negative flower structure or tulip structure. Okay. We didn't care about what's going on later. This example, normal example of structural fault. Don't care about it. We finished until this slide. We finished here. You have to focus what I said in this lecture because it's very important in exam. Okay. See you inshallah in next semester.